Okay everyone, now we're going to do the Lab 2 hardware. This one's going to be a bit tricky, so try to follow along as best you can. I'll try to guide you through it as best as I can. So the first circuit in this one is the diode connected NMOS here, figure 3A. And I've given you some nice Excel sheet for you to capture your data as well, and included the pictures. So I tried to make this as easy for you as I can, but unfortunately with the analog discovery module it's a bit challenging to measure current, so we'll have to work around that a little bit. So ideally there's two ways you can measure current here. The one that you would normally do if we were doing this lab at RIT is you break open the circuit at this point and you connect that to the multimeter, and the current will flow through the multimeter and you can measure it that way and get a easy direct measurement. Unfortunately, because these modules can't measure current directly, we have to follow a little different procedure here. So we insert a small resistor in series and we adjust this voltage, well, we adjust the supply voltage in order to get the VGS voltage that's required for the lab. So if VGS needs to be 2 volts, we'll have to set VDD to maybe 2.2 volts because there'll be some IR drop across the resistor. But since there's some voltage across the resistor, we can measure what the current is. If we set R equal to 100 ohms and there's 200 millivolts across it, we can calculate what the current will be just using Ohm's law. So instead of measuring current directly, we can measure the current that way, because the current that flows through the resistor is going to be the same current that flows from the drain to the source in this circuit here. And we'll also be adjusting this body voltage here. So it'll be a little challenging, but we'll get through it. So lots of data collection in this lab, but I've gone through all the steps to plot the data automatically for you. So you're welcome. Okay, so let's start with the diode connected circuit. Like I said, you'll need a resistor, and so I've chosen 100 ohms, which is brown, black, brown. Okay, and if I measure that, it should be close to 100. It's hard to do while holding my phone, so probably just trust me. Okay, it's 100 ohms, brown, black, brown. So I'm going to put this in my setup here. Now we need the ALD1103 chips for this, and I put pin 1 on row 5 here. This is pin 1, and the little notch is at the top. It's up at the top. So the NMOS goes drain, gate, source, and then body. The body terminal is shared on both sides. We only need to use one NMOS and one PMOS for this lab, so I'll just stick with the left side of the chip, except for when I need to connect the PMOS body, which is on the other side. So this is the diode connected one. I need to put my test resistor from the drain to somewhere else where it's not going to interact with the circuit, so I'll just put it in the top row. We need some wire to connect the drain and the gate together, so I got some little wires here that I'll just use just to try to make things clean. Hold on a sec. So I've connected rows 5 and 6 together. So that's the drain and the gate. The source is going to connect to ground. So I have my analog discovery set up over here. The ground is going to go to pin 3. And VDD, which is our variable input signal, that's got to go to the positive supply, which is red, the red wire. All right, so we're going to sweep back one. The other signal we need is the body voltage. So we need the body to increase. No, we need the body to decrease. So we need to use the negative voltage supply here. So V minus is the white wire, it looks like. Yep, white wire. So let me get a white wire over here to connect. And that's got to connect to the body, which is pin 4. Okay, so we got everything to power the circuit. Now we need to be able to measure voltage in a couple of spots. So I'm going to use the orange, which is channel 1, and going to set it up. Let's see, what should we measure? We want to measure VGS because that's what we are going to be wanting to sweep. So we'll put one on pin 1 and the other orange input on pin 3, VGS. All right, and that's basically it, I believe. So let's go back to here, and I still have waveforms up from earlier. Let's do the supplies. We're going to leave the negative supply off for now because we just want 0 volts. I don't know if it's going to like that. We'll see. The positive supply is going to be setting the positive supply in this circuit, VDD. So let's put it to 3 volts, I guess. And let's turn it on. And let's use the voltmeter. Run. See what voltage we get. 2.318 volts. So I've got 3 volts for VDD, which is here. And VGS is 2.318. So we can take the difference, use Ohm's law to figure out what the current is. So if I look back over here, there's a spot for VDD, and I have it set to 3 right now. We have to get the specified VGS values. So if we want 3 volts VGS, then I have to adjust this to let's see. It's pretty hard to do actually. So let's do kind of got to tune it in. So that's pretty close. So I needed 4.304 volts for VDD. In order to get 3 volts VGS. And so we can calculate the current as VDD minus VGS divided by 100. There's our current. Looks like Oh, this is in milliamps too, so we have to multiply by 1,000. Units are important, especially in this lab, because the plotting accounts for the units already, so make sure you follow what the column header says, milliamps. So 13.04 milliamps. Alright, there's a good chance that we're not going to be able to do the 3.5 and the 4 volt options because my resistor is a bit large. The highest I can go, if I go back here, if I set that to 5, I can get 3.34 volts VGS because I have 1.7 volt drop across the resistor. If you choose a smaller resistor value, possibly like 30 ohms, then you can get these last two data points here. But out of curiosity, let's see when the transistor starts to turn on. So if I reduce this down to 1.5 volts maybe. See the VGS, or not the VGS, but the VGS is following VDD much closer. There's not as much voltage drop across the resistor because there's less current. Well, if we drop this down to at 916 millivolts, there's 894 millivolts VGS. So the current's really small at this point. So somewhere around 0.8 volts maybe is where VT is. That's when the transistor starts to conduct. But as you do all of these data points here, that'll become more clear, and when these plots are constructed. Alright, so now the next thing we need to do is adjust VSB. So let's go back to here and let's turn on the negative supply. First I'm going to set this to, what do we have, 4.304 is what I found to be 4.30, somewhere around there, to get 3 volts VGS. If I make the negative supply 1 volt, then VT of the transistor should increase, which means the diode current, or not the diode, the MOSFET current will decrease, which means this voltage should increase here. And it looks like it did, because the transistor is conducting less current, so there's less IR drop across the resistor. So we can tune this in again. Let me try to get this to 3 volts. Looks like right around 4 volts. Okay. So I go to this one, and we needed 4 volts here, and we can implement the same equation. All right, and that gave me 10 milliamps this time. So the current did decrease by a bit. Next step is to adjust this to -2 volts, and again reduce this down further. Okay, 3.778 roughly. Oops. Didn't mean to do that. 3.778. And should see the current has decreased a bit some more. And it has. And so if you gather all this data, this plot doesn't look right now because I don't have all the data. But if you implement all the different VGS, VSB combinations, it will construct these plots for you, and it'll determine what VTO is, what KN prime is, and the body effect parameter as well. So these are wrong right now just because I haven't actually finished stuff. The next part is to do the same experiment with the PMOS. So I'll show you the wiring for that and quickly go through a couple examples, and then we'll move on to part 3. So let me turn off the supply and the multimeter. Master mode is off, master enable is off. And let's turn off everything, and I'm going to deconstruct the circuit. Okay, easy peasy. Now we got to do the same thing for the PMOS. So PMOS is wired the same way, drain gate source. In this case, the source is grounded, which was the case before actually. So let me get the black wire. And the source will be pin 11 for me. The drain and the gate are connected, which are rows 9 and 10. Okay, 9 and 10. And drain is going to go to VDD, and VDD is actually going to be a negative value in this case. So we need the minus supply voltage, which was the white one. So this is our VDD here. It's weird it's called VDD when it's negative, but whatever. And we need the resistor in between so we can figure out what the current is. So that goes from rows 1 up to rows 9, between rows 9 and 1. All right. The last piece is, so we got the full thing working. We just need the body connection, and the body is going to be a positive supply in this case, 0, 1, or 2. So the positive is the red voltage, and that goes actually on the opposite side of the chip if you look at the wiring diagram. So that goes to row 8, but on the right side, and it's the middle of the chip. NMOS body's on the left, PMOS body's on the right. Next thing we need is the measurement for VGS. So let's see, we'll put one here and one here. I think I got these backwards. Shouldn't matter too much, just changes if you get a positive or negative result. Okay. That should be good to go again. Go back to our setup over here. Now the negative supply is setting VDD in this case. So I'm going to set this to -3, and I guess you can't really, you just don't turn it on, the body. So we turn on the negative supply, master mode enable, and let's run the multimeter, see what we get. -3 volts gives 3.677 volts VGS. Alright, that might make sense. So we have to tune this again in order to get 3 volts, for example. So if I make this slightly larger, alright, looks like I got pretty close. So I needed 3.436 volts, or minus 3.436 volts in order to get 3 volts VGS. So I go back to here, 3 volts VGS, and this is 3.436. And it can be negative if you want, as long as you account for the polarity correctly, you're okay. This is VSG in this column, so you know, as long as you're careful, you're okay. And then you can calculate current the same way. So actually I'm just gonna copy the equation from before. Alright. And the PMOS should conduct less, so I'm not surprised that there's less current here. And you can probably get these last two data points for the PMOS with a 100 ohm resistor. The next part is you're going to get all those data points, then you're going to turn on the body effect with 1 volt. So it's going to make it harder to turn on, so you have to drop this voltage a little bit. Alright, and it's 3.338 for me now. If I increase this a bit more for the next points, and then you have to drop this further. In order to get 3 volts again. Minus 3.328. Okay, so basically doing the same thing you just did for the NMOS, just kind of in reverse for the PMOS. And again, that will calculate lambda, or not lambda, gamma, VT, and K prime for you. Alright, so the next part is this circuit here, which is also in saturation, but you're just sweeping it while it's in saturation. So we're basically looking at the output impedance. The output current shouldn't change a whole lot as we change VDS. We're keeping VGS constant here, so we can use this to figure out what lambda is. And again, we'll need the test resistor in order to figure out what the current is. So I'm going to put this back here and turn off the supplies and stuff, because we have to deconstruct our circuit again and go back to the NMOS. Alright, easy peasy. So this one we need the source grounded. So I'll get the black wire, drain gate source, row 7. Body is grounded. That's the row underneath it. Okay. And gate we keep at 2.5 volts, so we need the positive supply here. And we're going to set that voltage to 2.5. And drain, we'll connect that to our test resistor. Okay, and now this is a little tricky. We need a second positive supply. So what I'm actually going to do is move this one up to here. That'll be our supply that we sweep. And we need to generate 2.5 volts for the gate. So we should be able to use the waveform generator, I think, to generate a DC voltage. So that's the yellow wire. And I'll connect that to row 6. And we'll see if that works. Alright, let's give it a go. So back over here, we don't need the negative supply in this case. Let's turn on the gate first. So let's do wave gen. Channel 1 is the yellow output, and there is a DC option here. Let's just do 2.5 volts. Okay, And let's turn on this guy. The first data point is VDS equal to 2. So turn him on. Let's run our multimeter. And I think I forgot to turn on or set up the multimeter. So let's go do that real fast. Multimeter is the red, or the orange, sorry. And we just want to put that across VDS. So row 5 down to row 6, 7. Row 7. Okay. Now let's go back here. And looks like we got 2 volts in both cases. It's because my waveform turned off, I guess. Or maybe I just didn't enable it. Okay, so 2 volts on VDD. I don't know if you can see my mouse. 2 volts on VDD gave 1.232 volts on VDS. So again, we have to fine tune this. Can't get it. Somewhere around there, I guess. So 2.834 VDD gave 2 volts VDS. You can calculate the current as VDD minus VDS, in this case, divided by your resistance value, which is 100 for me. Whoops. And then you have to multiply by 1,000 to get the units right. So 8.34 milliamps. Kind of makes sense. And again, you're going to step through, you're going to adjust this guy. Looks like I can get up to 4 volts probably. So you're not going to get these last few points here just because we can't sweep the supply voltage that high. Unless we adjust this voltage here instead of ground, we could put it to a negative supply voltage and we could probably get things to work. But we won't go that far with it. We'll just fill in the first few points here. Should be able to get about half of this table filled. And I won't hold you accountable for not being able to do more than that. If you want to instead make this a finer sweep, instead of 500 millivolt steps, you could do 250 millivolt steps. That way you have the same amount of data. That's also good. It's up to you. Alright. And one thing to note is this current shouldn't change a whole lot. Ideally it's flat. It doesn't change at all with VDS. But it should increase very slightly as you go down this column. So just keep that in mind. If you don't see the current changing much, that's a good thing. It's not supposed to. Okay, the last circuit is the equivalent for the PMOS. So let's wire that up. Turn off our supplies. Turn off the multimeter. Alright, and let's deconstruct everything again. Last time. Now we got to use the PMOS again. Here, the gate is ground. So let me grab this guy. Gate is on row 10 on the left. VSS goes to 2.5. So we need a positive supply here. Actually, that's the source, goes to 2.5. And we'll use the measurement resistor again. Shouldn't matter which side you put it on, whether it's the drain or the source. They should be equal to each other anyways. Okay, so that is my positive 2.5 supply. The body terminal needs to connect to the source voltage. So I'm gonna need another wire here. It's got to connect over to here. All right, and what else do we need? Got to connect a variable VDD. Now the VDD is pretty tricky because at first it needs to be positive 0.5, then it needs to be 0, then it needs to be negative values from there on. So for a positive 0.5 volt supply, we have to use the waveform generator output to generate another positive supply. So I'll connect him there for now. Last thing we need is our measurement probes for measuring VDS. So we'll put this guy here, this guy over here. Alright, things are getting a little messy, but I connected that between the drain and the source. So rows 9 and rows 11 for measuring VDS. Okay, I'll try to move some of this out of the way. Alright. We'll come back to that in a second. So the positive supply, we need 2.5. We can turn that on, turn that on. Now we can run our multimeter, see what happens. And let's set the DC voltage here to 0.5 is our first data point. And run. And didn't seem to quite work. So let me see what the issue is here. So I got 0.5 volts on wave gen 1. 0.5 volts on W1. Oh, did I connect the wrong thing? Might have connected the wrong thing. Oh, I connected V minus here. It's not what we need. We need yellow. Which is right there. Okay. Sorry, couldn't see. I had the white wire going there. I needed the yellow one. Alright, so that looks better. Sorry about that. Still getting used to this thing too. Okay, so positive 0.5, we need to get VDS close to need to get VDS close to 2 volts. So why isn't it close already? Am I measuring the right spot? Let's see. Got drain and source. Drain gets waveform 1, which is 0.5 VSS, that's the source. Going to here. Oh, I had the resistor in the wrong row. That's what I get. That's what I get. Alright, now it looks like it makes sense. Okay, so yeah, my problem was I had the resistor in the row right above the red wire. So instead of being in row 18, it was in row 17. That was my mistake. Okay. So we can adjust, let's see, what can we adjust? We can adjust VDD, which is this voltage here, in order to get VDS close to 2 volts. So maybe 300 millivolts. Got us close. Oh, that was too far. Too far. Told you this lab was a pain. Oh, I was going the wrong way. So maybe about 220. $280. Alright, that's kind of close. So I had to set the supply to 0.28 in order to get roughly 2 volts VSD. So again, you can calculate with the resistance value. You can use that to figure out what the current is. Okay. That doesn't seem right. Doesn't seem right. I think there's a plus minus sign type of issue. So we put 2 volts VSD, and we put the resistor in, where do we put the resistor? Up to the positive supply. Okay. So this will be 2.5 minus, we measured VSD to be 2. So we gotta subtract off VSD, and we also have to subtract off VDD, I think. Equals 2.5 minus VSD minus that divided by 100, and then times 1,000. All right, 2.2 milliamps. Let me think about that for a second. I have to draw it out and make sure that that makes sense, what I inserted in there. And then I'll go over it with you guys. So the voltage here, you have to pretend there's a resistor in series here. 2.5, and you need the voltage on the other side of the resistor, which is whatever VDD is plus VSD, or VDS, whatever you want to call it. So VDS was 2 volts magnitude. So this was 0.2 and roughly 0.2. Yeah, 0.28. So 0.28 plus VSD, which was 2. So this is 0.28, 2.28. 2.5 minus 2.28 is about 0.22. Divide by 100, that gives you 2.2 milliamps. So looks like I implemented it right. So again, that equation for me is 2.5 minus VDD minus VSD divided by your resistance value, and then times 1,000 to get to milliamps. And I'll do another data point just to make sure that that works correctly. So we have to adjust this now even further lower than 0.28. And so we're going to have to use the negative supply here next. So I'm going to stop this. I'm going to turn this off for a sec. Turn off this. And now we're going to use the white wire in place of the yellow one and actually set it up correctly. Okay, like so. The white one should go right where the yellow one used to be, and it goes on row 9 for me. Same place as where I'm measuring with the multimeter or the voltmeter. Alright, so we don't need the waveform generator anymore because we don't need two positive supplies to use the negative supply, and we'll set it pretty low because we'll get one at the later points. Minus 3 volts. Let's turn that on. Click run. Alright, so at the last point we're looking for 6 volts VDS. So I can adjust this voltage here, the negative voltage, till I get 6 volts to measure on the meter. Alright, so it's pretty close. I had to set this voltage to minus 3.724. So minus 3.724 goes there. And see if I just copy this equation as is, if it works. And looks like it did. So like I said, the current shouldn't change much at all for this circuit. It should be very constant, and it looks like over that large VDS range I just tried, it was very flat. It changed by 20 microamps. Okay. And this will calculate lambda for you, as well as plot the data to the right. If I have more data points, it'd look nicer. Also to note, make sure you're getting pictures of your hardware setup as you go along here. I probably should have said that at the beginning. There's a summary table at the bottom which tells you all of the measurements, like the final result of all your measurements. What was K average, VTO, gamma, and lambda. None of these make sense for me because I didn't get all the data, but that's the idea. Alright, so sorry this lab's a little complicated, but I assure you the rest of them get a lot less tedious.